Hello. So I talk about marginal estimations this morning. Okay, so it's a shame you can't really see the formula, but the problem we are interested in is basically of computing the marginals of what is often called a graphical model. So you have dependencies in the variables that are encoded by a graphical structure. And so here you have, for instance, a probability of 4 variables that is assumed to be a product of factors that depend only on 3 variables. And so we want to estimate these local marginals, let's say P, ijk, ikl, when we look at 3 variables at a time. By beliefs, I will denote them by Q. So the little q's will be also local probabilities, but we don't know if they are consistent. Right. Ah oui, ok. Alors, ça marche pas quand je suis sur le flèche. Okay, so first I'll discuss a bit about the data structure that we are concerned with when trying to compute local marginals. And essentially, the main object consists of tensor fields. So it means, so I will denote by A0 this vector space, which is a direct sum of local tensor spaces. So each R to the power E alpha is the space of local functions on a Cartesian product. So each EI, all the components of the product can represent different atoms or different bits in signal processing. And so it's basically a dependent product type. So one way to think of it is that, or to implement it would be as a dictionary of tensors. So each entry has a shape that is prescribed. It could be known at compile time. And for each key, you have a different tensor. So of course, if you implement this as a dictionary, it will really not be efficient, but that's a good way to think of it. So for instance, for individual atoms, we'll have low dimensional tensors, and every time you add a variable, you get new dimensions for your tensors. So the dimension of this vector space here grows linearly in the cardinality of K. So that's the main idea behind using these structures, is that you get a linear dimension in the number of cells you consider. And what grows exponentially is only the dimension of each component, but you restrict yourself to small sets, E alpha. You only consider a few variables at a time. So you have natural maps between the different components of your dictionaries of tensors. Basically, they all come from the forgetful map. So here, for instance, on a 2-factor set, you just forget one component. And so because each tensor represents a space of functions on these local sets, so you have a pullback that is the inclusion of functions that depend only on xi, and functions, you can extend them on the product. It's a cylindrical extension. And so on the tensors, it just consists of repeating all your variables along the dimension. And the dual map of this extension is it consists of summing the values fiber-wise. It's just a marginal projection. And so you should think of this dual map. So it's it with a sigma, because it's a sum. You should think of it as acting on the dual of functions. So when you start summing things, f is more like a local measure. And so you have more maps, okay, because what I showed is that when you sum, it's just a fold, and the operation you use is the sum in the fold, but you could do other things before folding your tensor. So for instance, you recover conditional expectations. So given 2 tensors of different shapes, you assume here that pi is the marginal of pij. So you first multiply by pij, then you sum, and then you divide by pi, and this is precisely the conditional expectation. Okay, so it assumes you have these local probabilities. And another map that is very interesting is this one. I call it the effective energy. So before summing, you apply the exponential map with a sign. Then you sum, and then you take minus the logarithm. So it looks like a soft max, so here are these classical formulas. It looks a lot like a free energy, but you only sum on fibers of the projection. So it's more like a conditional free energy. And one very interesting thing is that you recover these conditional expectations just by differentiating this map here with respect to your local function. And so this is a very classical phenomenon that was really well known in thermodynamics, but here you get it at the vector level of local functions.
But for Gibbs measures.
So yeah, here, so you get that this conditional expectation here is the differential of the effective energy at Hij with respect to the local Gibbs measure. Okay, so the free energies, they generate the moments of the Gibbs states in this very general way. And so here you can really, everything is in finite dimensions. It's just the differential of this functional. This is a linear form on the space of local functions. Okay, so this is just the flat structure, if you like. But then we get topology, the simplicial structure, by considering the nerve of K. So I didn't really tell you what K is. It's just a collection of subsets. And in general, we only assume it is a semilattice for intersection. So the nerve of K is defined as follows. In degree 0, you only have nodes for all these nodes for each of your subregions. The nerve 1 consists of, because we had these natural maps and these arrows, we want to encode them and to consider them. So we're going to add new coordinates for all the arrows inside of K. And then the nerve, the second order nerve, it consists of looking at triangles, which are compositions of two arrows. You can go on. So this is a simplicial set. And if you now look at tensors indexed over the nerve, instead of looking only at tensors indexed over subcells, then you get a simplicial complex. Okay, and so this space of fields here, they are defined by sums over these chains, which are inclusions, sequence of inclusions. So your differential here, anytime you have an arrow here in your base category, then you take the difference of the tensor on the smallest coordinate minus the sum of your larger tensor. And you do this for every arrow. So on the right here, you have the set of keys is all these inclusions that are on the right. And so by duality, you get the dual map the other way around, which is a co-boundary. So the co-differential here consists, so maybe this part here is clearer. So when you want to evaluate the co-boundary in J, you will sum all the components that come from larger arrows. This arrow is terminating at J, so you count it with a positive sign. And this one is leaving J, this is going from J to the empty set. You take a minus sign. And so all the components that appear with minus signs, you have to extend them, pull them back by the projections, so that you can map them in your in the proper space. Okay. And so with this, now I'm going to talk a bit about this marginal estimation. That was the motivation for looking at these structures. And so here is a formulation of the marginal estimation problem. Very classical way. We consider here a probability distribution that is the Gibbs state of some energy function. And so this is also often called a graphical model, because assuming that your global Hamiltonian is a sum of local potentials, translates as a product for the probability density. Every probability density on a large number of variables can be written as a graphical model. You just have to take a large enough K. And the interesting thing here is that this H omega that lives in a very high dimensional space, here is described by a sum of local potentials, which all lie in small subsets. So if you look at the right-hand side, here it can be, well, it's a projection from this direct sum. And all these components, this space is of linear dimension with K, whereas the space of global observables here is of exponential dimension. Okay, and one of the things to first observe is that this map, this sum map, it's not injective. Okay, and one of the theorems. So one of the main theorems in my thesis was to understand that this the kernel of this total energy map is precisely the image of your boundary. Okay, so it looks a lot like ghost theorems in homology. So it's a very satisfactory result. And one implication is very trivial to prove because it's only the classical computation that you have these flux terms that cancel out when you add them inside the region. The other way around is much more difficult because these are functional equations in a larger dimension space. So you need to show that you can decompose, they have the same decomposition anytime you have a current here that relates the two. And another way to see it is that you have an exact sequence here. When you have your codifferential, it's exact because there is no cohomology. It's trivial. And here, when you sum, this is precisely, this part is exact. Okay. And so we want the marginals of this global distribution, and we understood better the parameterization. And so we look for things to approximate the marginals. So we look for consistent collections of local probabilities. And these are called beliefs, basically because they are local probabilities that may not be consistent. And because these marginals, these true marginals, they come from this marginalization factor from a very large probability density that you cannot compute. If you take the marginals of P omega, they will always be consistent and satisfy this consistency equation, telling you that Q beta is the marginal of Q alpha. But in general, when you're in this Cartesian product of local probabilities, you don't have this consistency equation. And so this is very easy to see from the previous definitions that this is precisely, if you take the minus sign here, it's precisely dq equals 0. So we get that consistent probabilities are zero cocycles. And I denote by gamma this set of consistent beliefs, okay? So it's included into a space of linear measures, and we just restrict. So gamma, this space of consistent beliefs, is really what we will use as a substitute for local, for true global probabilities that we could never compute anyway. And so here is a picture of the problem now. So we have this global observable H omega that gives you this global probability density here. But on the left part of the diagram, it's somewhere you really cannot go anywhere numerically because everything is of too high dimension. But instead, we understood that with this linear parameterization at the level of Hamiltonians, we understood that H omega comes from this low dimensional subspace of potentials, the local little h and little u, okay? And so we have this projection here, which is the homological projection that expresses that if I add any term delta phi, any boundary term, you preserve the total energy, hence the global Hamiltonian, hence the global probability distribution. So we are going to explore fibers of this projection. And we hope here we can define local beliefs by a local formula that mimics the global one. And we hope that the induced local probability distributions are consistent. But we have no way of defining this arrow. In fact, we may have multiple points satisfying this arrow. So we only have this arrow that we can compute, but we don't know if our local beliefs come from gamma. Okay? And our algorithm, they will try to implement at least approximately such an arrow if they converge. And so it's like to say that there are singularities on this problem, although it looks a lot like harmonic theory, because you have this. So this map, I'm not insisting too much on that, but this changes a lot of things because you have these sums. Now you are twisting these two adjoint differentials by this sum in the middle. So you don't have transversality of this space of solutions. So here is the manifold of consistent potentials. You project it onto homology classes that represents Hamiltonians. And so you may have you have a cuspidal singularity, for instance, in some loopy graphs. And so this means that you have unstable equilibria that will go to stable points. And so here is an example of numerical simulations that are leaving. So here, U0, when you leave, you are very close to you are very close to the surface. So you would expect the algorithm to converge back to the surface, but because this is unstable, you see here the distance from the initial condition that rises and stabilizes, and this is the distance from your surface. So it grows, and then it falls again because you reach a stable point. And so here are formulas for this diffusion. So we can write these just diffusion equations or transport equations. You will update your local potentials by a boundary term. And this term is really the analogous of a heat flux. Well, you can compute it this way with these natural formulas. A significant improvement was here to add a time step or a diffusivity coefficient. Because then when you look at the usual algorithm, these are the more usual formulas that are written at the level of beliefs. They are called sum product algorithm, because you have to marginalize local probabilities and then take a product. And this diffusivity coefficient here acts as an exponent. And it's very important. So BP was considered usually for epsilon equal 1 here, but it gets really unstable on hypergraph cycles if you don't take the care to have epsilon of order at least 0.5. It doesn't have to be anything small because you are only interested in the large time asymptotics of diffusion. But if it's too big or 1, then it may diverge. So thank you.